Welcome to Lecture 12 of the K105 course. We're going to do something different today. Call it exam prep. We will be reviewing areas that the class had some problems with on the last quiz, quiz 5. I'm not going to assign any homework or PT today, as I want to give you ample time to prepare for the exam. However, I would recommend doing homework number 10 and 11 before taking the exam. Talking a bit about the exam will be online. You can use calculators and note cards only. Do not use a phone or iPad to take the exam, as they may not work. If you had trouble accessing the exam last time from Blackboard, I would recommend using a different computer, perhaps one at school. The exam window will open at 12 noon on Sunday and will close at the end of the day on Monday. You will have 90 minutes to complete the exam. So now let's take a look at what we're going to review today. The first thing we're going to review today is complex numbers. You should have had discussions about complex numbers in some of your other classes. There's a prerequisite math course. Based on what I saw on the last quiz, I don't know how solid your backgrounds are in complex numbers. I'd like to just go over it again a little bit today, kind of give you kind of the feel of where it came from, how it's used, and just give you that kind of theory on it. Then we're going to transition. We want to transition from DC to AC. And we're going to then do a step-by-step procedure to calculate reactance, impedance, then setting up the circuit to solve. The next thing we're going to look at is how to correctly use the calculator. As I said before, it's a required calculator for the course. You need to really, if you don't have it, go out and buy it. They're $16 on Amazon. You order it today, you'll have it tomorrow. In time for the exam on Sunday, I really would recommend getting it and then getting familiar with it. We're going to go over it today. As I've said before, we all want to be on the same page on this. The other calculators you have, may work, but it's a whole different way that you use it, and it's not going to correspond to what we're doing here. And then we're going to go over every problem from quiz 5. And I put solutions up yesterday on Blackboard, so you can see that. You have a hard copy there, but I would like to go over them, and there's a lot of things missing from the solutions that may make it more helpful for you to understand what's going on in these problems. Okay, so let's first talk about complex numbers. So complex numbers are of the form x plus I y, and you probably haven't seen this before because it's not particularly important in this course, but I, which is imaginary, is actually the square root of minus 1. And so that's kind of a funny notion because what is the square root of minus 1? Well, what I'm just going to show you, it's like I said, it's not introduced in the class, and it's not needed to solve the problems that we're solving here because we have the calculator to solve the problem. But it is used if you apply algebraic solutions to these problems. So let me give you an example. Say we have x plus iy, okay, and then that's multiplied by another x plus iy, which will generate a quadratic equation. And you've seen these, x squared, so that would be plus I 2xy plus I squared y squared. So here's where the I squared will actually become a minus 1 because it's square root of minus 1 times the square root of minus 1 would be minus 1. So then this equation would become x squared plus I 2xy minus y squared. So I, which stands for imaginary, is used in mathematics. J is the same thing, but for whatever reason is used in electrical engineering. So the two are completely interchangeable. They both mean imaginary, and it means the square root of minus 1. What you want to do here is in electrical engineering we always use the J, as I said, and you can then express a complex number on the xy plane, and you've seen this many times in your math courses. We have x and y. Well, yeah, we saw x and y. Well, x becomes the real axis and y becomes the imaginary axis. So if we plot a point here, we'll have an x value, okay, and we'll have a y value, and that's in the coordinate system. And it is a plane, right? It's an x and a y, so it is a plane. These coordinate systems can have multi-axes. For instance, you could have a z out here too, okay, and where the axis would come toward you. You can have a multi-dimensional axis as well, but we don't need any of that right now. We're talking about a two-axis plane, okay, real and imaginary. Okay, so we can, as I said, we can express a point as an x and a y. We can also express that as a polar notation, which would have a magnitude and an angle theta. Okay, and this is what we call a vector, and we see this all the time in our problems. We have voltage vectors, we have current vectors, we have impedance vectors. So that's, I think, all I'd like to say about complex numbers. Now we'll talk about transitioning from DC to AC. So let's start with a simple example. You've seen this many times before. We have a voltage source here, DC voltage source. We have two resistors of the same value. For simplicity, I just wanted to show you this. So two 10 ohm resistors. We can calculate the total resistance for parallel combination. 1 over R total equals 1 over R1 plus 1 over R2, and that equals 1 over 10 plus 1 over 10. So 1 over R total equals to 2 over 10, which is 1/5. And if we do the flip to solve for RT, okay, RT equals 5 ohms. Okay, and if we want to calculate the current using Ohm's law, I equals V over R, so that's 20 volts over 5 ohms, and that equals 4 amps. So we basically have 4 amps in the loop here, and because we have equal resistor values, that current will split 2 amps into each leg. The voltage will be the same across it, right? The voltage will be 20 volts because this wire here is a common node to both resistors and the power supply, and the power supply would reign. That if it has the output impedance to drive that circuit and drive 4 amps, it would do so. I think in the lab you saw in the case where the power supply was limited, so you could not get the current that you expected to. In that case, the voltage would drop, and you wouldn't get 4 amps in the circuit, in this particular circuit. But for right now, this power supply can supply 4 amps, and this is basically what it would look like. All right, so if we look at the current of this DC circuit in the time domain, I should say, where we have time and we have current, we're going to just look at current. We're not going to look at voltage at this point. We know the voltage is the same across the resistor. So current would just be this. So at time 0, you turn the switch on, and it's going to be 4 amps forever and ever. Okay? So now, the next step is let's replace the DC source with an AC source. So if we look at the current in the resistors, we'd find that because we have a sinusoidal AC source at 60 hertz here, 20 volts AC, the current in the resistor would look something like this. It would be in phase with the voltage, of course, but it would be a sine wave, like so. And this would be IR1, and this would reach a maximum of 2 amps. Okay? And if I looked at the current in IR2, it would be, I'm sorry, in R2 I should say, it would, which is IR2, it would be exactly the same. Okay? It's the same phase. All right? So then if you look at the total current, which is I, it would look something like this. Still be a sine wave. It would be twice the amplitude. Nope, let me come back here. And we're going off the screen. That's okay. I think you get the idea. And this would be up at 4 amps. Basically, you could do an addition every point along here and plot that wave. So you'd have basically right at the peak here, you'd have 2 plus 2 and 4. So that's why you get the 4 amps. And so that sine wave would look like that, twice the amplitude of the 2. So now in this next case, let's replace the one of the resistors with an inductor whose value is J20, and we won't worry about the millihenry value right now. We'll just say that this is the impedance that we've calculated from the inductance, and we're going to call it J20. So we can use, again, parallel items. Now this is an impedance. It looks just like a resistance. So we can write the same equation, 1 over Z total equal to 1 over 20, which is the resistor value, and that equal to 1 over J20. And solving for Z of t, we can get 10 plus J10, and the current then is, and this would be the current vector, V over Z of t equals 20 over 10 plus J10, and that equals to 1 minus J1, which is 1 minus J. So you again using the calculator, and we'll be doing that shortly. For right now, I'm just going to show you what this will look like. So the current then is 1.414 at an angle of minus 45 degrees. The RMS value, let's see if we got some space up here. How about right up here? Now let's do it up here. It's got the wrong color. So IRMS equals the current peak times the square root of 2, and that would equal 4 times 0.707 and equals to 2.8 amps. So what I want to show you here is that if we look at the current in the resistor, it would look like just like it did before without the inductor in it. Okay, it would be a sine wave. Okay, going up to 2 amps. Okay, 2 amps. This is current here. And similarly, because we have an impedance of J20 ohms, if we remember Eli, right? Eli the Iceman. So the voltage leads the current. So in this case, the current will be delayed. So we would show that by a 90-degree delay because it's J. So this would be looking something like this. So this would be the current, and let's just start there. It would come up to the same value, but be shifted by 90 degrees. Okay, so now the reason why I showed you this here is that that's the value that this wave would maximize itself out at, which would be this point here. Everywhere else, if you added the two sine waves together, you'd have a lot of subtraction. So this is the maximum. That maximum is not 4 amps like we saw in the DC case. Let's see if we can go back there. Right. So right here we saw 4 amps because they added together at that they're in the same phase angle, so they're additive, and you get 4 amps. When we go to this case, they're out of phase by 90 degrees, and so we would never get up to 4 amps. But instead, it would look something like this. It would be a wave that would start here, still be a sine wave, which would be the sum of the two, and that would go up to only 2.8 amps. So hopefully this will give you a little more understanding and a visual of what's happening and why we can't just add currents one for one in an AC circuit as we can in a DC circuit. We have that phase shift, and this is how it looks. So now I'd like to walk through a step-by-step procedure to calculate the reactance and impedance of a circuit and then setting up a circuit to solve. And I kind of look at this as kind of a cookbook. If you follow this step by step, it'll set your problem up properly so that you'll get to the right answer. So let's start with a circuit, a simple circuit. You've seen these before. So we have a voltage source, AC source, 60 hertz. In this case, we have 2 inductors, L1 and L2, and 1 resistor. So step 1, convert inductance and capacitance values to reactance, to their reactance, which would be X sub C or X sub L. X sub C is the reactance for a capacitor. X sub L is a reactance for an inductor. So for L1, it would be, remember, 2 pi FL is the equation, and this is x sub 1, x sub L, I'm sorry. So put that in your on your note card, and this in this case would be 2 pi times 60 hertz, the frequency, times the inductance 0.005 Henry, and that equals 1.89 ohms. So that's L1. Okay, so the reactance of L2 would be similarly 2 pi FL, and that equals 2 pi times 60 hertz times 0.033, and that equals 12. Let's back up here. That equals 12.4 ohms. And remember, reactance is only a magnitude. Okay, it is not. It has no direction to it. It's not a vector. If this were a capacitor, the capacitor reactance would be 1 over 2 pi Fc. We've seen this before too, so put that equation on your note card. Okay, so next thing we do, we'll call it step 2. We're going to solve for, or we're going to convert the reactances to impedances. So we have a reactance, and that we're going to make that an impedance. So for excuse me. So the impedance of L1 is equal to, simply putting a J in front of it, 1.89 ohms. And the impedance for L2 is equal to J 12.4 ohms. So we just added a J in front of the reactance. Now what we want to do is remark our circuits so that they're no longer millihenries, but now they're impedances. J 12.4 ohms, and this one goes to J 1.89 ohms. Step 3. Solve for the total impedance of the circuit, Z of t, Z total, and that is a vector. So Z of t equals J 1.89, which is the impedance of the first inductor, because we're basically writing a, let's go back to this. We're going to say that this inductor is in series with the parallel combination of this resistor and this inductor. So we can write that as 20 plus 20 ohms, which is the resistor, and that's in parallel with the impedance of the second inductor, which is 12.4. So the way we want to attack this, we want to solve this first to simplify and combine those two elements, because then we can say that it's just two elements in series with one another, and that's easy to solve. So we'll say that this parallel combination here is 1 over, whoop, we lost our color here again, 1 over, we'll call it ZP. ZP is the parallel combination, is 1 over 20 plus 1 over J 12.4. And we can use our calculator now to solve that. And just make sure that the calculator is in the complex mode. That's mode 2. Puts it in complex mode. So now we can solve this equation. So the way we'll enter this is we'll put in a 20 and take the inversion of that because it's 1 over 20, and then plus, and here's where I use parentheses because we're working in the complex plane, and when we invert that, it might only invert part of it. All right, so we have plus, and that's 12.4, and we have to hit the little I here, close parentheses, and then we'll invert that, and we'll get the answer, hit equals. Okay, and there's the value, and now we have to invert both sides of the equation to solve for ZP. So we'll do an inversion on the answer, equals. So there it is. So this equals 5.55 plus J 8.9. So if we bring this together with the impedance of the other inductor, this will equal Z total will equal J 1.89 plus from here 5.55 plus J 8.9, and that equals 5.55 plus J 10.8, and this is ohms. This will be represented in the circuit as a simplification of the circuit, as we talked about. So here's the first inductor, and this could be the inductor and resistor could be replaced just with an impedance block. Okay, and this would be 5.55 plus J 8.9 ohms. Step 4. Solve for other circuit parameters using Ohm's law, current divider, or voltage divider. And I would refer you to the previous video. That's last Monday's video. We do a lot of examples there showing how to solve for different circuit parameters using Ohm's law and the voltage divider. For today, I'm just going to say that for this one, if we want to solve for IS, the source current, we could say that, and that's a vector, V over Z, and that equals 120 volts over our impedance, which is 5.5 plus J 10.8. And again, I'll go back to the calculator here. I already have the impedance in there. We want to invert that, and then times 20 volts, and we'll convert it to decimal notation. So the current is 1, whoop, keep hitting that, 1 minus J 1.61, and that's so putting in polar notation, we hit shift 2 3 equals, so this becomes 9.8 amps at an angle of minus 63 degrees. So now we're going to go over quiz 5. So let's look at problem 1. Problem 1 wants to know if the power factor can be greater than 100%. And the answer is false. It can't be. And here's why. If you remember our triangle, power triangle here, we have true power, we have reactive power, and we have apparent power. Okay, the power factor equation, which you should write on your note card as well, is true power over apparent power times 100%. So apparent power it can be only greater than or equal to true power. So if you look at this triangle, because it's the hypotenuse, it can only be greater or equal to, right? So the power factor is always less than 100%. The second question wants to know what the voltage is read by a handheld meter, voltmeter, like the one we use in the lab, looking for the RMS voltage. So that RMS voltage, when you have a magnitude and direction, say we have x volts at an angle of theta. Okay, this value here in polar form is the RMS value. So what they've given us here is an impedance, a voltage voltage vector that has imaginary and real parts in it at 60 hertz. Well, 60 hertz isn't really needed here because it's already an impedance. 60 hertz would have been used to calculate the reactance to generate the impedance. But it's already done here. So the 60 hertz is superfluous information at this point. So we're just going to take our calculator and we're going to convert the linear or the rectangular form of this to the polar form, and that's all we have to do. So it's 163.8 plus 14 or 114.7 I, and if we then use our shift 2 3 equals, so that becomes equals 199.96 at an angle of 35 degrees, which is the answer. It's 200, approximately 200, but it's 199.96. In problem number 3, they're looking for us to convert circuit values to impedances. So we have a 47 microfarad capacitor. So again, compute the capacitive reactance first. So X sub C equals 1 over 2 pi, and they're giving us 60 hertz as the frequency of the system, times 0.12347 microfarads, and so that equals to 56.4 ohms. The reactance, the impedance, is minus J, 56.4 ohms. Okay. For the inductor, So x sub L equals 2 pi 60 frequency times 0.082 henries, and that equals to 30.9 ohms. Okay, and the impedance of the inductor would just be J 30.9 ohms. And for the last one, well, that's easy. It's a resistor. It has no frequency has no effect on it, so it's just a resistor, 330 ohms. So for question 4, this is a time constant problem. They want to know, want us to calculate the voltage on the initially uncharged capacitor 3 seconds after the switch closes. So for that, we use the time constant equation, V, in this case the capacitor, you want to know the voltage on the capacitor, as a function of time equals Vs times 1 minus E to the minus T over tau, where tau, this is tau, equals an RC time constant. So in this case, R is 10 ohms, and C is 0.5 farads, so that time constant is 5 seconds. Okay, so now we can plug that in, and we can say V of the capacitor, and the time we're interested in is 3 seconds, so we're looking for T at 3 seconds equal to Vs, which is 8 volts DC, times 1 minus E to the minus T, which is 3 over tau, which is 5. And you can run your calculator and solve that very easily, and that comes out to 3.61 volts. So for question 5, they're looking for us to calculate the complex current for the circuit. And complex means it's got real and imaginary parts, right? And for full credit, they want us to express the current in the polar form. So what we'll do here, we have this circuit. It's 120 volts at 0 degrees and 60 hertz. They've given us step 2 here. They've already calculated the impedances for us. They didn't give it to us in microhenries or microfarads. They've given us the impedances. So they've done step 1 and 2 actually for us. So now we're at step 3, and we're going to calculate the total impedance of the circuit. And this is a series circuit, so we can just go around the circuit like so. So it's 5 ohms plus J2 minus J5. So that's the impedance vector, and calculating the current vector equals V over Z, the impedance total, and this is a vector as well, so that would be 120 volts at 0 degrees over 5 minus J3. So we can now calculate this with our calculator. So we'll take 120 divided by, and we'll use our parentheses, 5 minus 3i, close parentheses, and that equals, and we can convert that to decimal. So that's 17.6 plus 10.5i, and now they want us to convert that to a polar form. So we can hit Shift 2, 3 equals, we'll go to decimal. So that's approximately 21 at an angle of 31 degrees. In problem 6, they're giving us two vectors. They're giving us a voltage vector of 120 volts at 0 degrees and a current vector at 2 amps at minus 60 degrees. So this is an Eli problem, right? ELI. So that's saying that voltage is leading the current. So that's an inductive circuit. So it's inductive. Whoop. I'm having trouble with my pad here today. Okay, there's an inductive circuit. The next part of the problem, they want to calculate the impedance. So the impedance is V over I, and that equals 120 over 2 at an angle of 60 degrees, minus 60. And again, we can use our calculator to determine that. I'll let you do this one. It's 30 plus J 5.2 ohms. And then they want the power, complex power for this circuit, or for these vectors, which is V times I. And that's I star. That's the complex conjugate of current. So that would equal 120, an angle of 0 degrees, times 2 at an angle of 60 degrees. And here's where we change the polarity of the angle right here. That's where the complex conjugate of the current comes in. The current was 2 at minus 60, but now as the complex conjugate, it becomes 2 at plus 60. And that equals 120 plus J208, and that's in volt amperes. In problem 7, we have an RLC circuit, and they're just looking for the total impedance. So, step 1, convert all of the circuit elements of capacitors and inductors to capacitive and inductive reactions. Okay, XL equals 2 pi times 60 times 0.047, and that equals 17.7 ohms. XC equals 1 over 2 pi 60 times 100 microfarads, and that equals 26.5 ohms. Again, those are magnitude only, and we're now going to convert those to impedances. So Z of L equal to 17.7, or J 17.7, and the next thing we can do is some circuit simplification here. So we'll redraw this circuit as an inductor, in series with the resistor. We just moved the inductor to the end, to the side here. Now they're in series, but now it's going to be easy to write an equation for that. So if we say we do have a parallel combination of the capacitor and the inductor and the resistor in series, so we can say Z 1 over Z total. Again, this is step 3, equal to 1 over J 26.5, which is the capacitor impedance, minus J, plus 1 over, and here's our resistor of 56 ohms in series with the inductor, which is J 17.7. So we can use our calculator to solve this now. So we'll put in parentheses 26.5 I. I'm sorry, that's minus 26. Let's back up here. Impedance of the capacitor would be minus J 26.5 ohms. So now we can replace L1 with J 17.7, and C1 becomes minus J 26.5. And that equals, and then to get the impedance, we have to invert both sides. We'll invert that again. So that equals 12.2 minus 24.5, J 24.5 ohms. So there's your answer. And finally, for the last problem, this is an efficiency problem. So basically, you're given some efficiencies here. We have a AC to DC converter, and then we have a DC to AC converter, AC, ultimately running a motor. And really what you do is you multiply these efficiencies across. So the total efficiency and total equals, call it N1 times N2 times N3, and this would be 0.97 times 0.92 times 0.85, and that equals 0.759. So that's the total efficiency through that system. Just multiply them together. So the next thing we want to do is look at our power out, in that we have a 3/4 horsepower motor, and we want to convert that to watts. So we have a 3/4 horse, 0.075 horsepower, and we'll use our conversion factor. Hopefully you have that on your note card, 746 watts per horsepower, and that equal to 560 watts. So now we can say efficiency, we know is power out over power in, and we want to find power in, so this becomes power in equals efficiency times power out. Efficiency is 0.759 times whoops, I made a mistake here. Let's cross that out. And it's P in equals P out over efficiency. And that's P out is 560 watts over 0.759. And that is equal to 740 watts. So now we can just calculate the current equals 740 over 208, and that is equal to 3.6 amps. Well, that's going to do it for today. I know it was kind of a long session. Hopefully we got through the problems you've had understanding some of these problems and how to solve them. And I just hope it was worthwhile. We did spend a little extra time. But anyway, good luck on the exam on Sunday and Monday, and we'll see you next time.